Welcome to the deep dive. Today we're jumping into something really fascinating, the foundations of artificial intelligence.
Yeah, getting into the nuts and bolts. We want to understand how we're trying to build these, intelligent machines.
Exactly. And we've got some great source material here that really lays out the groundwork. So the plan is to dive in, pull out the key ideas, and hopefully leave everyone with a much clearer picture of what AI is all about at its core.
Right. We'll cover the history, different kinds of AI, the main ways people are trying to build it, and how we even try to figure out if a machine is smart.
Sounds good. We want to give folks a solid understanding without, drowning in jargon.
Precisely.
Yeah.
Connect the dots from the past to the present, get the core principles down.
Okay, let's start at the start then. AI feels so current, so futuristic, but the idea itself, it's got deeper roots, doesn't it?
Oh, absolutely. The field of AI is relatively young, maybe mid-20th century onwards, but the dream of making intelligent machines goes back centuries. A really good place to start is actually the word robot. Ah, okay. Where does that come from?
It was coined by a Czech writer, Karel Upbeck, back in 1920, in his play RUR.
R.U.R. Rossum's Universal Robots. I know that one. So robot comes from Czech.
Yeah, it means essentially forced labor or drudgery. The play was about these mass-produced artificial workers, sort of tapped into that whole anxiety and excitement about automation even then.
Wow, forced labor. That's quite an origin. Puts a different spin on it. But you said the ideas go back even further.
Much further. I mean, think about ancient Greece. Aristotle, in the Politics, was already wondering about tools that could work on their own.
Really? Aristotle.
And then fast forward to the 13th century, you have Ramon Lull talking about, like, automatic reasoning with symbols, and Leonardo da Vinci.
Wait, Da Vinci, what did he do?
He actually sketched designs for what looks like a mechanical knight, a kind of robot. It shows this wasn't just a philosophical idea. People were trying to build things, too.
That's incredible. Da Vinci's robot? Yeah. And then you have philosophers like Thomas Hobbes thinking about reasoning as just a form of computation. And of course, all those amazing old automata, the mechanical ducks and music boxes.
Right, like Vaucanson's duck. I've seen pictures. Amazing craftsmanship.
Exactly. Frederick Vidoni's anus was inspired by that duck. All part of this long history of wanting to automate, maybe even replicate, life and intelligence.
So long fascination. But what were the big intellectual shifts, the things that made AI possible as a science?
Okay, yeah. That's where logic and computation come in big time. You've got Gottfried Leibniz in the 17th century. He had this vision of a calculus of reasoning.
A calculus of reasoning. What does that mean?
He imagined a universal language, a lingua characteristica, where you could basically translate arguments into symbols and then just calculate the answer, solve disagreements with math. Calculemus, he said. Let us calculate.
Wow, so turn thinking into calculation. That sounds very AI.
It's a core idea, right? Then, much later, George Boole comes along in the 19th century.
Boolean algebra. That rings a bell from, like, school math.
Exactly. And that system, with its true-false, on-off logic, became the absolute bedrock for designing electronic circuits, telephone switches, and eventually, computers.
Even though Boole himself wasn't necessarily thinking about computers?
Probably not in the way we know them, but he knew his work was significant. His logic provided the mathematical language needed for computation. It bridged that gap from abstract ideas about reason to something you could actually potentially build.
Okay, so we have the logical framework. What happened in the 20th century to really light the fire?
The mid-20th century was just explosive. 1943, you get McCulloch and Pitts. They published this paper on a logical calculus of ideas immanent in nervous activity.
Okay, break that down for me.
Basically, they proposed a computational model of a neuron, a mathematical description of how a brain cell might work in terms of logic. Hugely influential.
But mathematical neuron, that sounds like the direct ancestor of neural networks today.
It really is. And then, just a few years later, 1949, Donald Hebb writes, The Organization of Behavior. He proposes this idea that learning happens in the brain when connections between neurons get stronger the more they're used.
The neurons that fire together, wire together idea.
That's the essence of it, yeah. Hebb's rule. That became fundamental for thinking about how AI systems could learn from experience, adapting their own internal structure.
So the theoretical pieces are falling into place. Was there a moment when it all sort of Coalesced, became a field.
Many point to a symposium at MIT in 1956, Symposium on Information Theory. It brought together all these people working on related problems from different angles: psychology, linguistics,
Who
computation.
was there? Any big names?
Oh, yeah. George Miller presented his famous magical number 7 paper about memory limits. Noam Chomsky was there, talking about his early ideas on grammar and language structure.
Chomsky.
And crucially, Alan Newell and Herbert Simon demonstrated a computer program that could actually prove theorems in logic. That was a real wow moment. Proof that machines could do things that seemed to require intelligence.
A program proving theorems. That must have been mind-blowing back then.
Absolutely. And you also had Claude Shannon, the information theory guy, thinking about AI too. He wrote a paper in 1950 about programming a computer to play chess.
Chess, right. That's always been a benchmark for AI, hasn't it?
It has one of the earliest challenge problems, and of course none of this happens without the hardware.
The computers themselves.
Right, you need the machines.
Yeah.
Charles Babbage's analytical engine, way back in the 19th century, was conceptually groundbreaking, even if it wasn't fully built then.
A mechanical computer, essentially.
Yeah. And then, critically, in the 1930s, you get the theoretical work of Alonzo Church and Alan Turing.
Turing, the Turing machine.
Exactly. Turing's theoretical machine and Church's work on recursive functions basically defined what computation is, what is theoretically possible for a machine to compute. The Church-Turing thesis is still fundamental, this idea that any computation can be done by a Turing machine.
So that sets the theoretical limits or capabilities of what AI could potentially do running on these machines.
Precisely. It's an amazing journey from, ancient automata to the abstract power of the Turing machine. It all lays the groundwork.
Okay, that's a fantastic overview of the history. Let's switch gears now to the present day, or at least how we categorize AI now. We hear different terms thrown around. What are the main types?
The biggest distinction, the one you hear most often, is between narrow AI and general AI.
Narrow versus general.
Okay.
Sometimes called weak and strong AI, right?
Exactly. Weak AI is narrow AI, strong AI is general AI. Understanding this split is key to understanding where we are now and where the field hopes to go.
Let's start with narrow AI then. What's the deal there?
Narrow AI is basically AI that's designed and trained for one specific task. It might be incredibly good at that task, maybe even better than humans, but that's all it does. It can't generalize.
So like a specialist.
Exactly, a super specialist. Think about early systems like ChatGPT, which could answer questions about a specific database, or expert systems like MICIN, which helped doctors diagnose bacterial infections.
Or prospector for geology.
Right, or Deep Blue playing chess. IBM even argued Deep Blue wasn't really thinking like a human, just calculating incredibly fast within the rules of chess.
Okay, so very powerful, but in a very defined box. What else falls under narrow AI?
Oh, tons of stuff we use every day. Speech recognition on your phone, that's narrow AI. Recommendation engines on Netflix or Amazon, narrow AI. Even those early self-driving cars, like Stanley in the DARPA challenges, great at driving in certain conditions, but couldn't, suddenly decide to write a poem.
Right, got it. Specialized tools. So what's the ambition with general AI then?
General AI, or artificial general intelligence, AGI, is the goal, still hypothetical really, of creating a machine that can perform any intellectual task a human can.
Any task, wow.
Yeah, it's about replicating that flexible, adaptable, general-purpose intelligence we have. The ability to learn, reason, solve problems across totally different domains. Our sources call it the ongoing quest for human-level artificial intelligence, or HLAI.
That sounds much more like the AI we see in sci-fi movies. Are we anywhere close?
That is the million-dollar question, isn't it? There's a lot of debate. Even decades ago, people like Hillary Putnam were asking, what's the big fuss if AI hasn't really achieved general intelligence yet? It's still a huge challenge.
And this is where things like the Chinese room argument come in, right?
Sure.
Questioning if even sophisticated mimicry counts as real intelligence.
Precisely. John Searle's Chinese room thought experiment is a classic philosophical challenge to strong AI.
Remind me of the setup again.
Okay, so imagine someone locked in a room who doesn't speak Chinese. They have a huge rulebook. Someone slides questions in Chinese under the door. The person uses the rulebook to find the right Chinese symbols to slide back out as answers.
Okay.
To someone outside, it looks like the person in the room understands Chinese. But Searle argues the person inside is just manipulating symbols according to rules they don't understand a word of Chinese.
So the argument is that a computer running a program, even one that seems intelligent, might just be manipulating symbols without any real understanding.
That's the core of it. It questions whether simulating intelligence is the same as possessing intelligence or consciousness or understanding. Our source material kind of hints that maybe understanding is something that happens at the whole person level, not just symbol processing.
It really makes you think about what understanding even means.
It does, and related to that is the idea of AI complete problems.
AI complete.
Yeah, it's the idea that solving certain problems, like truly understanding natural language and all its ambiguity and nuance, might actually require having full-blown human-level general intelligence already. You can't solve that one problem without solving the whole AI problem.
Okay, that makes sense. Understanding language requires understanding the world, basically.
Pretty much. So this narrow versus general distinction is fundamental. Most of what we have now is narrow AI, even if it's getting very sophisticated. General AI remains the long-term, very challenging goal.
All right, so we know the history, we know the main types. How do people actually build AI systems? What are the main strategies or approaches?
Broadly speaking, we can talk about three main camps, though the lines blur quite a bit these days. There's the symbolic approach, the sub-symbolic approach, and then hybrid approaches that try to mix them.
Symbolic, sub-symbolic, hybrid. Okay, let's take symbolic first. What's the philosophy there?
Symbolic AI is often called top-down, or sometimes cheekily a UFAI, good old-fashioned artificial intelligence.
UFAI, I like that.
The core idea is that intelligence can be achieved by manipulating symbols, words, concepts, facts according to explicit rules, like logic. You basically try to encode human knowledge and reasoning processes directly into the machine.
So you're programming in the knowledge and the rules for thinking.
Exactly. Think back to those early pioneers, Newell and Simon, with their logic theorist program. It worked by representing logical axioms and theorems as symbolic structures, and then applying rules to transform them and find proofs.
Okay.
Or Gelernter's geometry theorem, prover. Or Newell and Simon's later general problem solver, GPS, which tried to model human problem-solving strategies using symbolic representations of goals and actions.
What are some other examples of this symbolic approach?
Evans's program for solving geometric analogies was a classic example. It used really complex symbolic descriptions of shapes and rules for transformations. And SHRDLU, Terry Winograd's program that could talk about a world of blocks.
SHRDLU, right. It understood commands like pick up the red block.
Exactly. It had a symbolic model of its little world. Expert systems like Mycin and Prospector are prime examples too, built on hundreds or thousands of if-then rules representing expert knowledge.
Those lots of rules.
Lots of rules. Planning systems like strips also use symbolic logic to represent world states and actions. And semantic networks.
Semantic networks. What are those?
They're a way of representing knowledge as a graph, like a web. Nodes represent concepts or objects, and links represent the relationships between them. Like a node for canary linked to bird with an is-a-link, and linked to yellow with a has-color link.
Oh, okay. Like mind maps almost.
Sort of, but more formalized. Early systems like SIR use them, and the idea underpins big knowledge bases like WordNet, which maps out word meanings, and Psych, which tries to encode common sense knowledge. Rule-based systems and cognitive architectures like Sager also fit firmly in this symbolic tradition.
Okay, so symbolic AI is all about explicit knowledge and rules. How does the sub-symbolic approach differ? It sounds like the opposite.
It pretty much is. Sub-symbolic AI, also called connectionism or bottom-up AI, doesn't focus on explicit symbols and rules. Instead, it emphasizes learning patterns directly from data, often using models inspired by the structure of the brain, specifically artificial neural networks.
Neural networks. Okay, this feels more like modern machine learning.
It's the foundation for much of it, yes. Instead of programming in the rules, you create a network structure, feed it lots of data, and let it learn the patterns and relationships itself.
How did that start?
Well, remember McCulloch and Pitt's modeling the neuron, and Hebb's ideas about learning by strengthening connections? That inspired early researchers like Clark and Farley to experiment with a neuron-like computing elements. Then Frank Rosenblatt developed the perceptron in the late 50s.
The perceptron. That was an early neural network.
Yeah, a simple type designed for pattern recognition. Adeline was another early one. There was a period, sometimes called the AI winter, where enthusiasm for neural nets cooled a bit.
Why was that?
Well, early models like the perceptron had limitations in the kinds of problems they could solve. But then in the mid-1980s, there was a huge resurgence.
What caused the comeback?
Two big things. The development of more sophisticated network architectures like multi-layer networks, and crucially, the invention of the backpropagation algorithm.
Backpropagation, that sounds important.
It was huge. People like Rumelhart, Hinton, and McClellan were key figures. Backpropagation provided an efficient way to train those deeper multi-layer networks, allowing them to learn much more complex patterns. That really kicked off the modern era of deep learning.
So neural nets learned how to learn better.
You could put it that way, yeah. Other related ideas like Hopfield networks and Boltzmann machines emerged too, and we started seeing practical applications like the LVN system using a neural network to steer a vehicle.
Wow, autonomous driving back then.
Early days, but yes. And other machine learning approaches like reinforcement learning, where systems learn through trial and error, getting rewards or penalties, like with Q-learning, also fit under this broad subsymbolic umbrella. Learning from data, not explicit rules.
Okay, that's a clear contrast. Symbolic is top-down rules, subsymbolic is bottom-up learning from data. What about the hybrid approach, combining them?
Exactly. As the field matured, people realized that both approaches had strengths and weaknesses. Symbolic systems are often better at explicit reasoning, planning, and incorporating existing knowledge, but can be brittle and struggle with messy, real-world data. Subsymbolic systems excel at pattern recognition and learning from data, but can be black boxes, hard to understand why they make a particular decision, and sometimes struggle with high-level reasoning.
So, Hybe tries to get the best of both worlds.
That's the goal. Many modern AI systems incorporate elements of both. For example, the HACE-PICIP system for ocean surveillance used a blackboard architecture. Yeah, it's a system design inspired by Hearsay 2, which was good at handling noisy signals. It allows different modules, potentially using different techniques, some symbolic, some subsymbolic, to cooperate on solving a problem by sharing information on a common workspace, the blackboard. It suggests mixing structured problem solving with data analysis.
Interesting. Any other examples?
CALO, the Cognitive Assistant Project, used something called Markov logic, which explicitly tries to combine first-order logic, symbolic, with probabilistic graphical models, subsymbolic. In computer vision, it's common to combine symbolic models of objects with subsymbolic image processing and machine learning to recognize things in pictures. Even Bayesian networks, which are probabilistic, can incorporate structured, symbolic-like prior knowledge.
So it seems like the trend is towards more integration, using the right tool for the right part of the problem.
Definitely. It reflects the complexity of intelligence itself. It likely involves both structured reasoning and pattern recognition, learning from experience.
Okay, so we have all these ways of building AI. How do we know if we're succeeding? How do we measure AI intelligence? That seems like a really slippery concept.
It is incredibly slippery, and it's one of the longest-running debates in the field. But the most famous attempt to provide a benchmark is, of course, the Turing test.
The Turing test again, proposed by Alan Turing back in 1950.
Right. In his paper, Computing Machinery and Intelligence, it's less a rigorous test and more a thought experiment, really, designed to sidestep philosophical debates about thinking or consciousness.
So what's the actual test? How does it work?
The classic setup is the imitation game. You have a human interrogator, a human participant, and a machine participant all separated. The interrogator types questions and receives typed answers from both the human and the machine.
Without knowing which is which.
Exactly. The goal of the interrogator is to figure out which one is the machine. The goal of the machine is to fool the interrogator into thinking it's the human. If the machine can fool a typical interrogator a significant fraction of the time,
Then it passes the test.
then, according to Turing, we should consider it intelligent, or at least capable of intelligent behavior. It focuses purely on observable conversational ability.
But it's controversial. People argue it's not a true test of intelligence.
It's hugely controversial. Turing anticipated many objections in his paper, but critics argue things like, well, the Chinese room argument suggests you could pass the test just by manipulating symbols cleverly without any real understanding. Others say it's too focused on deception and human-like conversation, and maybe intelligence can manifest in other ways.
So it's a famous benchmark, but maybe not the definitive answer.
Uh-huh.
Are there other ways people try to measure AI progress?
Yeah, definitely. A lot of evaluation is task-specific. Like we mentioned, chess programs get rated using the same ELO system as human players. AI systems for image recognition are benchmarked on standard datasets for accuracy. Performance in robotics competitions, like the DARPA challenges for driving, provides concrete measures.
So measuring performance on specific capabilities rather than general intelligence.
Often, yes, it's more practical. And remember, IBM's stance on Deep Blue, they won the chess match, a huge feat. But they were careful to say it was about massive computation, brute force search, not human-like intuition.
Right. No formula exists for intuition. So high performance doesn't automatically equal human-style intelligence.
Exactly. And there are things like the Loebner Prize, which is an actual competition based on the Turing test, but even its results and significance are debated. It's still a really open question. How do we meaningfully define and measure artificial intelligence?
It really brings you back to square one, questioning what intelligence itself even is.
It does. And as AI gets more capable, these questions only become more pressing.
Wow. Okay, this has been a fantastic deep dive into the foundations. We've really covered a lot of ground.
Yeah, we've gone from, Papex robots and Leibniz's calculus right through to neural nets and the ongoing debates about general AI and the Turing test.
We hit the history, the key distinction between narrow and general AI, the main ways of building it symbolic, subsymbolic, and hybrid, and the tricky business of measuring it all.
Hopefully it provides a solid framework for understanding all the AI news and developments we see today. Knowing these foundations gives you context.
Absolutely. So maybe a final thought for our listeners to chew on.
Yeah.
As we see these different approaches, the symbolic, the subsymbolic, the hybrids, how do you think they might eventually lead to something like general intelligence? Or is something completely different needed?
That's the big question, isn't it? Are we on the right path, just needing more data, more computing power, better algorithms within these paradigms? Or does achieving truly human-like flexibility and understanding require a fundamentally new idea, a different kind of architecture we haven't discovered yet?
Something to ponder. What are the limits of the current ways of thinking?
Exactly. It invites you to think critically about the claims being made and the challenges that still lie ahead. We encourage everyone, if something sparked your interest, a historical figure, a specific system, the philosophical debates, definitely dig deeper.
Great advice. Well, thanks so much for unpacking all of that.
My pleasure. It's a fascinating field.
It certainly is. Thanks, everyone, for joining us on the Deep Dive. We'll catch you next time.